Hello. In this video, we're going to be talking about units again and what to do with cubes and squares when we convert those into different dimensions. So if you have a ruler, I would encourage you to pause this video and grab that ruler because you're going to need it or at least want it. So go ahead and pause and get that. First thing we're going to do is draw a 2-inch by 2-inch square. So you'll see the 2 there. So I'm drawing a 2-inch by 2-inch square. And I think when it comes to units, it really helps to imagine what we're talking about. You know, you could solve a problem that has inches and centimeters, right? So here's 1 centimeter up to this 10 mark. The little dashes are millimeters. So 10 millimeters is 1 centimeter. We'll talk more about centimeters and meters in a second. But this is 2 inches by 2 inches. And if I ask you what the area of this is, we know that area is width times length, or just the 2 sides. So we'd have 2 inches times 2 inches. This is very much like 2y times 2y. So again, we're going to treat the units like we treat variables or like we treat numbers. So if we had 2 times 3 times 2 times 3, we could say that this is 2 squared times 3 squared. This would be 2 squared times y squared, or 2 squared times inches squared. So notice the units get squared. Okay. If we do it with numbers, we do it with the units as well. Or more conveniently, we would say that the area is 4 inches squared. So that's one example. If we were to now think about a cube, so I should have left myself more room, but we're going to redraw our 2 by 2 square and then also make it a cube. And we make it a cube by making a 2-inch depth. So again, I would encourage you to draw that using actually 2 inches if you've got your ruler. Mine's a little wonky, but for the sake of argument, let's say that's 2 inches and that's 2 inches. So that's our square from before, but now if it had some dimension, some depth to it, and we make that 2 inches as well, we could ask what is the volume of this? So a square is just the surface area. A volume has depth. Most of the things we deal with in the physical world, even a sheet of paper, has some depth to it. It's small compared to the length times the width, but it does have some thickness to it. So we're really talking about the thickness. We could often represent, you see these represented with little dashes to try to imply the receding depth. And if we asked what the volume here would be, we would say it will be 2 inches, or length times width times depth, times 2 inches, times 2 inches. I guess this should be height times width times depth, something, those 3 coordinates. We'd have 2 times 2 times 2 inches. So here again, we see that we have 2 cubed, 2 times 2 times 2, and then inches would also be cubed. 2 cubed is 8. So we could say that the volume here is 8 inches cubed. Volumes will always have some kind of cubic dimension, cubic, cube. So it's not coincidental. The very word cubic in many ways implies 3 dimensions. So we can use language to our advantage in that case to make understanding. Sometimes we just use words like cubic and not really understand why every time we see a 3 as an exponent, we talk about cubic. But there is a connection to actual cubes. So let's look at another example. I'm going to stop doing these with rulers. And let's say we have 2 inches there. I'm sorry, 2 inches here. I'm going to try to make this a little bit longer. We're going to make that a 4-inch depth. And let's say it was 3 inches tall. So we have a 2 by 4 by 3. So in this case, we'd have 2 inches by 4 inches by 3 inches. And if we were asked for the volume of this, then the volume would be 2 times 4 is 8, 8 times 3 is 24, and we'd say the volume is 24, inch times inch times inch, or cubic inches. So now we've got a volume that's 24 cubic inches. So let's say the problem says, what's the volume of this cube in centimeters cubed? Because a lot of times we deal with the metric system in science. So we want to get out of the American system of inches and feet and miles and into the system that the rest of the world uses, which is the metric system: meters, millimeters, centimeters, kilometers, kilograms, grams. Okay? So let's say the problem is to convert this volume. So again, we're talking about the volume. How much space does this whole thing take up? The 3-dimensional volume that's represented. But do that in cubic centimeters. How many cubic centimeters would fit into that volume? Well, one way we could do this is to convert each individual side. So we could say, well, 2 inches, let's convert that into millimeters. Well, what's into centimeters? What's the conversion? Well, you might not be familiar with it, but if you look at this ruler, this is 1 inch. So maybe I'll even try to zoom in. Well, I can't zoom in, but I can pull this closer. So there's 1 inch. And notice opposite 1 inch, we have centimeters. Centimeters are the big tick marks here. So there's 1 centimeter, there's 2 centimeters, and about a 1/2 centimeter to an inch, a little bit more actually than 2.5 centimeters. So the actual conversion between inches and centimeters is one that I would expect you to know starting college. And if you don't know it, now's a good time to learn it because it's a very useful one. There are 2.54 centimeters is equal to 1 inch. So if I draw a line that is 1 inch long, or I draw a line that is 2.54 centimeters long, so there's 1 centimeter, there's 2 centimeters, there's 2.5 centimeters. Those two are the same thing. That's what we mean by this very equal sign. It says this length is equal to that length. Now notice 2.54 is not 1, 2 different numbers, but 2.54 centimeters is equal to the same thing as 1 inch. Just like 100 cents is equal to $1. 100 is not 1, but when we add the unit, the critical unit, you get an equality. Okay, so we can use this conversion now. If we want to convert into centimeters, we're going to put 2.54 centimeters in the numerator over 1 inch. How do I know which way I want to arrange that? The answer is simple. I don't. I figured out based on getting units to cancel. I want the inches to cancel, so inches have to be in the denominator. So this length in centimeters would be 5.08 centimeters. We're going to do the same thing for the other 2 sides. We have 4 inches for one of the sides, same conversion factor, 2.54 centimeters to 1 inch. That's 10.16 centimeters then, because the inches cancel. And 3 inches times 2.54 centimeters per inch is equal to 7.62 centimeters. Just want to double check that. Yep. Inches cancel inches. So now we've got that. And now if we wanted to, we could, get the volume, and we would say 5.08 centimeters times 10.16 centimeters times 7.62 centimeters. And you get 393 centimeters times centimeters times centimeters, so 393 centimeters cubed. So what it's really saying is if you had a box that was a centimeter big on each side, so a centimeter by a centimeter by a centimeter, you could fit 393 of those cubic centimeters into this volume. Okay. So that's one way to do it. And notice here we had to do this conversion 3 times, right? And if we had something to the 5th, we'd have to do it to the 5 times. And if we had something to the 9th, we'd have to do that conversion to each thing 9 times, right? So it gets to be a pain. So you would say, isn't there an easier way? And in fact, there is an easier way. And I'll show you where it originates. So we'll prove to ourselves what we're about to do. If we look at what we did above, we said 2 inches times 2.54 centimeters per inch. And that came out to be the 5.08. So then we took that 5.08 and then we multiplied it by 10.16. Oops. We took that 5.08, multiplied by 10.06, but that was just 4 times 2.54. And then we multiplied by 7.62, but that was just 3 times 2.5. So really we could rewrite this as what we did as that, right? And that would still be equal to the volume. And now I'm going to break out those things that have similar units on them. So we could go back to 2 inches times 4 inches times 3 inches as one cluster, and then everything is multiplied, so we can still say times 2.54 centimeters per inch, that's that one, times 2.54 centimeters per inch, that's that one, times 2.54 centimeters per inch, that's that one. But remember what we said, whenever we have, x times x times x, that's equal to what? X cubed? Well, this whole thing would be 2.54 centimeters per inch. And here's the key thing. That whole quantity would be cubed. It's not just the 2.54. It's not just the centimeters. It's not just the inches. So if we write this as 2.54 centimeters cubed over inches, that's not the same thing. X times y over z cubed is x cubed times y cubed over z cubed. But if we write x times y cubed over z, then we're not cubing the x and the z. So these are two different statements. The parentheses are really important here. So I'm going to cross out those things that are wrong. 2.54 centimeters per inch cubed. This whole thing would come back to what we saw before, 8 times 3, 24 inches cubed. So now our volume would be 24 inches cubed. That's the volume we originally calculated. And now notice what happens. We can say times 2.54 centimeters per inch. That's going to get our inches. But because the inches here are cubed, we know that we need to cube that whole conversion factor. So rather than converting each individual side and doing it 3 times, we're just going to do it in one fell swoop here, recognizing that when we do this calculation, we have to take 24 and multiply it by 2.54 cubed, and that the cube applies to the centimeters and that the cube applies to the inches. So the inches are going to cancel the inches cubed, and we're going to be left with 24 times 2.54 cubed centimeters cubed. And if you take out a calculator and you plug in 2.54 and you cube that number and you multiply by 24, you get 393 cubic centimeters, the same answer as we got before. So the take-home message here is that when we have units that have exponents on them and we are converting them into different units, we need to cube or square the conversion factor 2 when we do the conversion. We wouldn't just say 24 inches cubed times 2.54 centimeters per inch and just do that multiplication, because that would get us 24 times 2.54, 60.96, which is not the right answer. We saw what the right answer is when we did the individual sides, 393. So we have to recognize that this whole thing would need to be cubed because the units are cubed. And it all goes back to, we had to do the conversion 3 times. We had to multiply by 2.54, we had to multiply again by 2.54, we had to multiply again by 2.54, and all that showed up there, just like it showed up here 3 times. You would have multiplied 2.54 3 times. So that's a fact, that's a manipulation that a lot of students miss, that if you square or cube a conversion term, you also have to square or cube, I'm sorry, if you have units that are squared or cubed, you have to square or cube the conversion factor. So please practice that and remember that when you start in class. So here's a problem then that we'll work on, that I would encourage you maybe to pause the video and see what you can do. Imagine that we're looking at an Olympic swimming pool, bird's eye view of an Olympic swimming pool. So, here's a swimmer, they're swimming around, they're doing a race. Olympic swimming pools are 25 meters by 50 meters length times width. And we could ask, what is the area? So the first thing that we're going to do is figure out the area in meters squared. But after you figured out the areas in meters squared, what I'd like you to do is figure out the area in feet squared. That looks like a fraction. It's not a fraction. So first task is area in meters squared, then in feet squared, then in inches squared, and then finally D in centimeters squared. And to help between this conversion, I will tell you that 1 meter is 3.28 feet. So if you think about 3 feet tall, like I'm personally 6 feet tall, so I'm about 2 meters tall, because 2 meters would be about 6 feet, a little bit over. Not quite 2 meters, be a little bit shorter than that. But so if that helps, think about your own height. If you're 5 foot, you're somewhere between 1 and 2 meters tall. So go ahead, pause the video, use this conversion factor, go from meter squared to feet squared, then from feet squared to inches squared to centimeter squared, and see what you can do with that once you pause the video. Okay. Hopefully you worked on those and have answers. It's much more instructive to commit yourself to an answer and then see if you're right or wrong than it is to just wait for somebody else to do it. I use the analogy in class that it's like riding a bicycle. I can watch somebody ride a bicycle and I can think, oh, that's pretty easy. All I got to do is remember to balance and pedal and steer. How many of you were successful the first time you tried to ride a bicycle? Watching somebody do problems is exactly like that. You can watch me and go, oh yeah, I get that. I think I could do that on my own. But it's until you have to generate it on your own and string ideas together that you begin to see where you might not have everything down pat. Just like when you started riding a bicycle, you thought, oh, I can balance, but really most of us couldn't the first time. So it's okay to have to go back and look at notes and things, but it's really important to try to do it on your own prior to exams, prior to the week before exams, because it's that constant practice that's going to help. So let's start with A, the area in meters squared. 25 meters times 50 meters gets us an area of 1,250 meters squared. We want to write the units, because if I just say the area is 1,250, that's not so impressive if the area is 1,250 millimeters squared or nanometers squared. Right? If it's 1,250 miles squared, that's a big difference between 1,250 millimeters squared. So the units tell us something. If I just came up to you and I said, I'm going to give you 50,000, Are you excited or not? No, you don't know, because you don't know if I'm giving you $50,000 or 50,000 pebbles of sand. Right? So the units tell us more than the actual number itself, quite honestly. So now, to get that into feet squared, we're going to take 12,050 meters squared. We have this conversion factor. Which way do we want to set it up? I don't know. I can either say 3.28 feet per meter, or 1 meter is 3.28 feet. Both are legitimate conversion factors. Well, in this case, we want the meters to cancel. So I'm going to use the 3.28 feet, because now I know that those are going to cancel top and bottom. Meter squared cancels the meter squared. I would have to take 3.28, square it, and multiply by 1250. So in other words, this is 1250 times 3.28 times 3.28 times feet squared, or I calculated 13,448 feet squared. I hope that's the right number. If not, please email me or tell me and I'll correct this video. Well, I'll just double check it because I don't like getting things incorrect when I can avoid it. Get enough things incorrect when I can't avoid it. Okay, 13,448 feet squared. Now we can go to inches squared. 13,448 feet squared. We know that there are 12 inches in a foot. That's another conversion factor. These two things are equal. 12 inches is equal to 1 foot. If I walk a foot or I walk 12 inches, I've walked the same distance. So this ratio is really the ratio of two things that are equal. If we take two things that are equal and divide them by each other, what do we get? We get 1. So this is really a statement that's equal to 1. If we multiply by 1, we don't really change it. We're just expressing it in a different way. So we're converting it to different terms. 1 squared doesn't change the number either, but we have to square this to get the conversion correct in terms of feet squared, get the units to cancel. So then we take 13,448 times 12 times 12, and we get 193,600, oh no, oof, sorry. 1,936,512 inches squared. 1,936,512 inches squared. Sorry, that's getting pretty messy. Now, last thing, if we want to go to, I guess this is D, into centimeters, 1,936,512 inches squared. Earlier, we saw that there are 2.54 centimeters per inch. So hopefully you went back in the video if you didn't remember that conversion and looked it up, because a lot of colleges going back and looking stuff up that you don't know, but you might be expected to know, or using the textbook to find out information and conversion factors. Times 2.54 times 2.54, and I get 1.25 times 10 to the 7th. So notice I'm going to slip into scientific notation. 1.25 times 10 to the 7th. Inches cancel, and now we'd have centimeters squared as our units. Inches squared canceled, we squared the 2.54, and we are left with units of centimeters squared. So this swimming pool is 12,050 meters squared, or we can also say it is 1.25 times 10 to the 7th centimeters squared, or we could say it is 1.9 times 10 to the 6th inches squared, or we could say it is 1.35 times 1.34 times 10 to the 1, 2, 3, 4 times 10 to the 4th feet squared. All are equivalent. We're still talking about the surface area of the pool, just expressed with different units. So notice the number changes because the units are changing. Okay. Coming back to this problem, I want to show how we can string conversions together. So if we wanted to convert from 2,050 I'm sorry, from 1,250 meters squared through all of these different conversions, we can now also start writing them in a way that's going to make it a lot faster for solving problems on exams. So I'm going to start with that 1,250 meters squared. I'm going to say the first conversion we did was feet to meters or meters to feet. We multiplied those two. And then we took that number and we multiplied by 12 inches per foot. And then we took 1 inch is 2.54 centimeters squared, and that should have been squared as well. So notice what we would have to do now in calculating. We deal with the numbers first. Numbers would be 1,250 times 3.25 squared times 12 squared times 2.54 squared. You plug that into your calculator, you get 1.25 times 10 to the 7th. Unit analysis now, we'd have meters squared times feet squared over meters squared times inches squared over feet squared times centimeters squared over inches squared. So all I'm doing is abstracting each one of those units. Meter squared cancels meter squared, feet squared cancels feet squared, inches squared cancels inches squared, and we've got centimeter squared. So we know we have the right units that were asked for, and we know that we have the right number because we squared all of those terms. It is, of course, possible if our goal was simply from meter squared to centimeter squared to recognize that there are 100 centimeters in a meter, 100 centimeters per meter, just like there are 100 cents to a dollar. So centa is key or codes for 100, and then we'd have to square that. So we would be taking 1.25 times 10 to the third times 10 squared centimeters per meter and squaring that. 10 squared, 10 to the second squared is 10 to the fourth, centimeter squared, meter squared, 1.25 times 10 to the third times 10 to the fourth. And if you remember some things about exponents, we said we add exponents together. We'll see that when we have scientific notation, we do the same thing. So 10 cubed and 10 to the fourth is going to be 10 to the seventh. So we get 1.25 times 10 to the seventh centimeter squared. I'm sorry, the meter squared would have canceled, and we'd be left with centimeter squared. Okay. So we arrive at the same answer if we just wanted to go directly to centimeters. But this shows that we can string conversions together. It's a lot faster to solve problems that way. And I encourage you in the early days of general chemistry, even if you know how to do problems by chunking them up and doing a lot of individual manipulation, practice stringing things together like this because it'll make you a lot faster at solving problems on exams. A lot of students struggle with problem solving fast enough on exams to make sure that they have enough time to check their work. So it'll be an expectation that you work quickly through exams or work efficiently through exams. You don't want to rush, but you want to find efficiencies. And I think this is an efficient method rather than writing down each individual step and doing each individual conversion on its own. This is a lot faster. So try it. If you're unfamiliar with it, you have now and the first couple weeks to try some things. As I mentioned earlier in the first or second videos, I hope to be putting some problems up, maybe even problems from previous exams that you can practice on to get good at doing these kinds of things so that when we start learning chemistry on top of the math, we're not bogged down by problems in math that get in our way of learning the chemistry. Okay. So we'll do other things in coming videos, other strategies for doing well in class, logic exercises, hopefully coming up too. So hope you are having a good summer despite all of the craziness that is. And again, look really forward to seeing you on campus and have a good rest of your day.